Yeah, I'll spend the next half an hour or so talking about neural networks. And so let's just get going. A neural network is a function. It takes in a value and outputs a value. And in some ways, a neural network is a particularly simple class of function because it's mostly just doing addition and multiplication. But in other ways, it's also a very complicated function because, as Moy and Carey mentioned, um, neural networks often have millions or even billions of parameters. But nonetheless, at the end of the day, it's still just a function. And so a natural question to ask is, how powerful are functions? Let's see what the mathematician Thomas Garrity has to say about this.
Functions describe the world. Everything is described by functions. The sound of my voice on your eardrum, function. The light that's kind of hitting your eyeballs right now, function. The entries you put in your random matrices, function. It's all function. Different classes in mathematics, different areas in mathematics study different kinds of function. High school math studies second degree one variable polynomials. Calculus studies smooth one variable functions. And it goes on and on. Functions describe the world.
Okay, wow. So I admire his passion, but is he right? For example, think about the problem of recognizing objects in a photo. Does there really exist a function where you feed it the pixel values of any image, and that function can tell you what objects are in the image? Is there really an equation, that you could write on with a pencil on a piece of paper, equation with x's and y's that could actually do that? Before the deep learning revolution, many scientists would have said no. Identifying objects in images or summarizing texts seemed beyond the reach of mathematics. But neural networks have proven that there are, in fact, mathematical expressions that can do these things. And neural networks can discover what those equations are. So how do neural networks work? Let's take a look at their basic architecture. Some of this has been covered previously, but I thought I'd just go over the basics of the architecture. Let's say we're building a network that will learn to predict the price of a house using certain criteria. So neural networks have an input layer, one or more hidden layers, and an output layer. In this example, there's just one hidden layer, but most neural networks have multiple hidden layers. The input layer is where data enters the neural network. In this example, the input layer contains data about a house and its surroundings, such as the size of the house, the number of bedrooms, the number of trees per square mile in the neighborhood, let's say, and the noise level of the area. This is just a dummy example. You would probably want a lot more features than that for an actual model. But in this example, the features of a house are fed into the network, and the neural network uses these features to predict what the price of a house might be. Hidden layers are where most of the data processing happens in a neural network. That's where a lot of the multiplications and additions that I mentioned earlier take place. And each hidden layer takes inputs from the previous layer. It transforms those inputs in a way that I'll explain later, but that's just addition and multiplication, really. And then it outputs a single value which gets passed onto the next layer. And finally, the output layer is where the neural network generates its prediction. So for tasks like predicting house prices, the output layer consists of a single node. But the number of nodes in the output layer depends on what kind of problem the neural network is trying to solve. For example, a neural network that recognizes handwritten digits will have an output layer with 10 nodes, not just one node. And each of those nodes represents one of the digits. So in this case, each node in that output layer outputs a number which represents how much the neural network thinks the digit is a 0 or a 1 or a 2 or a 3, etc. Okay, so we've seen the basic architecture of a neural network. Now let's look at how you train one. Let's continue with the house prices example. To train the neural network, we'll provide it with a whole bunch of examples, but in this table, I'm only showing 4 training examples. Each row in the table is a single training example, but normally you would have hundreds or thousands or tens of thousands of training examples. In the first row, we see a house that has the following features. It has 1,500 square feet, 3 bedrooms. There are 50 trees per square mile in its neighborhood, and the neighborhood during the day, let's say, has a noise level of 40 decibels. And in the last column of the table, we see what the actual price of the house is. That's the price, the actual price in the real world. So training a neural network consists of 3 steps: forward propagation, computing a loss, and then back propagation. And forward propagation is the process of feeding a training example through each layer of the neural network to obtain a predicted output. A loss function then measures how good or bad the prediction is compared to the actual value, and then back propagation begins. Back propagation adjusts the weights of the neural network to make better predictions the next time the network sees the same training example or similar examples. It treats the weights of the network like they're dials that you can turn up or down to improve the network's performance. And so training of a neural network is a loop where you feed it a training example into the input layer. The network then does forward propagation, computes a loss, and then back propagation happens. And that's when the weights of the network are adjusted. You then feed a new training example into the input layer and repeat the loop. And you repeat that loop many times over the training data, and make passes through the training data more than once, like many times, the same training data. You repeat that loop many times over the data until the loss gets really small. So let's take a closer look at what happens inside a node during forward propagation. Let's zoom in on this first node in the hidden layer and see what it does. We're looking at this particular node in the hidden layer, but all the nodes in the hidden layers do the same thing. So when I'm talking about what's happening in this node, I'm talking about what's happening in all the nodes in the hidden layers. So here's a zoomed in picture of the node. You can see that it receives the 4 features of a house: its size, number of rooms, number of trees, and noise level, as we've seen. And this node, like every node in the network, has a unique set of weights. Notice that the number of weights matches the number of nodes in the previous layer. So we have 4 pieces of data coming in, so this node needs to have 4 weights. And the node multiplies its 4 weights with the 4 values coming into it from the previous layer. It then adds up those results, and the result is a single number, which appears as Z1 on the slide. The node isn't quite finished, though. It then adds a bias term, and I'll talk about what the bias term is later on. And then finally, the node applies an activation function to the total. And I'll also talk about activation functions in a little bit. In this example, we're using the ReLU activation function. So let's zoom back out and show the network as a whole. It's important for you to know that every node in the network has its own unique set of weights and its own unique bias. And each node performs the calculations I showed on the previous slide. So I thought we would go through an example here. Node 1 receives the data about a house, and it performs its computations. And let's say it outputs a single value of 6.1. Node number 2 then receives that exact same input data that node number 1 received, and it performs its own computations with its own unique set of weights, and it outputs, let's say, a value of 0. And then node number 3, again, receives the same input data. It does its thing and outputs a value of 2.3. The node in the output layer receives the 3 values output by the hidden layer, and it performs its own weighted sum. So in this example, let's say it outputs the number 9.1. 9.1 is the neural network's prediction of the price of the house in hundreds of thousands of dollars. So in other words, the neural network's prediction for the house price is $910,000. Now let's take a look at step 2 of the training process, where the network computes a loss. The neural network uses a loss function L to get a sense of how good or bad its predictions are. In this case, the loss function we're using is the equation you see on the slide. It's called the mean squared error loss. And this loss function looks at the difference between y, which was the neural network's prediction, and the actual price of the house, and it squares that difference. So in this case, the prediction was 9.1, but the actual price of the house was 4.5 in hundreds of thousands of dollars. And so in this case, the loss is 21.2. Squaring the difference ensures that the loss is always positive, and it has the added benefit of amplifying larger errors. So it gives the neural network a larger slap on the wrist when its prediction is particularly bad. And so then the last step of training is backpropagation. And that's where, as training goes on, you're going to see the loss function decrease because the network's predictions improve. And so that error of 21.2 will get smaller as training goes on. And the reason that loss function decreases is thanks to the third and final step of training, which is backpropagation. And backpropagation is probably the most interesting part of the training process, because during backpropagation, the network's weights are updated so that, I think I mentioned earlier, the next time the network encounters the same or similar data, its prediction will be more accurate. And so the line of code you see here is really where the magic happens. This is how the weights are updated. And so this really is how the neural network learns over time. In this case, we're looking at the weight W1. And for those of you who remember grade 12 calculus, this line of code decreases the weight W1 by the derivative of the loss function with respect to W1. So each of the weights and biases in the network are adjusted in this way. And the Greek symbol you see on the slide is the learning rate. It controls how big the update to W1 is going to be. This number is a constant that the programmer who's training the model defines. It's usually a number like 0.001 or something like that, a very small number, so that the weight is only adjusted a little bit. So to make this a little more concrete, because I talked about calculus there, let's say that the loss function looks like this. The horizontal axis represents different values of a particular weight, like W1, let's say. And the vertical axis tells you how much loss we get when W1 is a certain value. And so the goal of backpropagation is to incrementally adjust W1 so that we get closer to the minimum of the loss function. And so here, the tangent to the curve at a particular point W1 is the red line that you see there. And its slope is that derivative term dl dW1. And the slope of that tangent line is negative. So in this case, the line of code is going to be subtracting a negative number from the weight W1, which means we're adding a small number to the weight in order to get closer to the minimum of the loss function. So if that math was a bit hard to follow, calculus might seem like a long time ago for some of us. Here's sort of the takeaway that, or an easier view of it, things. So if the derivative of the loss function with respect to a weight is negative, that means we're on the left side of the loss function. In other words, the tangent line on the left side of the graph has a negative slope. And so in that case, back propagation is going to add a small number to the weight W1 in order to get closer to the minimum. But if the derivative is on the other side of the loss function, if the derivative of the loss function with respect to the weight is positive, that means we're on the right side of the loss function. And in that case, back propagation will subtract a small number to the weight to get closer to the minimum. And so this is how, over time, the weight W1 inches towards its optimal value, which actually, in this case, is its optimal value. The minimum is at 0, which is a bit odd. I guess the neural network has determined that this weight is actually pretty useless, and it wants to zero it out. It says, I'm going to disregard this weight. Okay, so I went through a lot of information there, so let's just pause for a bit and just go through some questions. So the first question I have is, how many weights are in this neural network? And I'll give you like half a minute or so to think about that. Or, you could put your answer in the chat. Okay, I will put you out of your misery because I know everybody's really keen to know. So Dave and I think it was Pamela got it, right? It's 15 because each of the nodes have a unique set of weights. So this one has, sorry, just a sec. So the first node has 4 weights. That node also has 4 weights, and those weights are different than the first node's weights. And the last node in the hidden layer also has its own unique set of weights. But let's not forget the node in the output layer, which will have 3 weights, because there are only 3 nodes. There are only 3 weights in that node because there are only 3 nodes in the previous layer. So the total number of weights in the network is 15. Okay, so let's, question 2 is, how many bias terms are in the neural network? And I'll give you a little bit of time to think about that. Okay, so the answer is each node in the network has a unique bias term. So the answer is that there are 4 bias terms in the network. And then next question, what are the 3 main steps in training? Here, I'm wondering if you remember what the steps in the training loop are. Yeah, Terry got it. Forward propagation, computing the loss, and back propagation. And then the last question is, what computations does a node perform during forward propagation? Wow, that's, maybe I won't ask people to respond there because there's a lot, it's very mathy. So the answer is the node multiplies each of the inputs from the previous layer with its set of weights. It then adds up all those multiplications adds the bias term, and then applies an activation function to the sum. And then that node, remember, just outputs a single number to all the nodes in the next layer. Okay, so let's briefly talk about the importance of the bias terms and the activation functions. Here again is that slide which shows a zoomed in view of what a node does during forward propagation. When I showed this slide earlier, I said I'd explain what the bias term is, and that's that blue term in the equation there. You can think of the bias term as a way to shift the output of a node up or down regardless of the input values. This can be important in certain situations, but not always, because usually the input values into a node typically have a big influence on what that node's output is. So to explain, let's go back to our example of the neural network that predicts house prices. Imagine the bias term in the output node or somewhere, one of the nodes, is the base price of a house in the area, no matter what features that house has. So even if a house is really tiny or has no bedrooms, or it still has some value because of it's a house, and maybe because of its location, let's say. So the bias term in the output node captures this minimum price. In other words, as soon as something is called a house, its price is automatically $55,000, let's say, regardless of its features. Because price, yeah. So if you look at the graph, you'll see that the house price line crosses the y-axis at around $55,000, even when all the feature values are zero. So it's like saying the cheapest house isn't $0. Instead, it's this base price of $55,000. So having a bias term allows the network to learn better because it separates that base price from the impact of specific house features. And so making sure each node has its own bias term often makes the network simpler and allows it to train faster and to predict more accurately. So now let's just briefly look into why activation functions are important. The final step, if you remember, in the node's computation is to apply an activation function to the weighted sum of its inputs. And that's that pink term that you see there. So why are activation functions important? To explain, let me show you another example. Let's say the housing data looks like this. Without activation functions, you actually can only fit a straight line to the data. But if nodes use activation functions, the network can fit more complex nonlinear curves to the data. So basically, an activation function is used to introduce nonlinearity into the network so that the network can learn more complex patterns in the data. And these are just some examples of really common activation functions. The sigmoid function, which is the graph, there's a graph of it in the top left corner there. That just squishes input values to be between 0 and 1. Tanh is also just another squishing function, but this time it squishes things to be between -1 and 1. And the ReLU function, which is shown as the hockey stick shape at the bottom left of the slide, has become actually really popular in recent years. It outputs a 0 for negative inputs and outputs the input value itself for positive inputs. So basically, it makes negative values 0, and then it just, if the value coming into the node is positive, it just maintains its numerical value. And then the leaky ReLU function is similar to ReLU, but it's just a slight alteration. Okay, and then this last section of the talk is, can you interpret how a trained neural network works? So neural networks are often considered black boxes because it can be very challenging to understand how they arrive at specific predictions. As we've seen, they often have a large number of nodes and layers, which means they have millions or billions of parameters. And this makes it difficult to understand the steps of their reasoning. But people want to be able to interpret the reasoning behind a neural network's output. That's important for building trust in the model's predictions, especially in domains like healthcare and finance and the legal system. So, for example, people want to understand why a neural network denied them a mortgage or how it arrived at a particular medical diagnosis. So to illustrate how a neural network makes predictions and how we might interpret its reasoning, let's consider an example of a neural network trained to recognize handwritten digits such as the MNIST dataset. In image processing tasks, the early layer of a neural network learns to detect simple features such as edges or textures. And Carrie mentioned this earlier when the model that she showed was trying to detect faces. At first, it would just, you can think of that first hidden layer as looking for very primitive shapes in the image, like straight lines at different angles or just slightly curved lines. For example, in this example, the handwritten digit is being fed into the network. The first hidden layer might find the 7 primitive shapes you see on the slide in different colors. And those primitive shapes combine to form the digit 9. As we move to deeper layers, the neural network can combine these simple features to detect higher level attributes. So in some cases, the second hidden layer might detect more complex shapes like circles or long vertical lines. But sometimes the layers are not interpretable in the way that I just showed. It's not always possible because often the features that hidden layers detect aren't actually interpretable by humans. And so making these systems more interpretable is a very active research area. And that's it. Here's just a summary of what I covered. Neural networks are powerful functions that are capable of solving really complex problems that people thought previously that were beyond the reach of math. And the architecture of a neural network consists of an input layer, one or more hidden layers, and an output layer. Training a neural network involves 3 main steps: forward propagation, computing the loss, and back propagation. And activation functions are crucial components that enable neural networks to fit complex nonlinear patterns in the data. And finally, briefly talked about, how can we interpret neural networks? It's a really challenging thing to do right now because the features learned by the network may not always be human interpretable. And that should be it. I'm wondering if people have questions or Rick.
Yeah, great presentation, Chris. Thank you. That really helped me understand some things that I did not understand before. I was curious, why are they called hidden layers? Do we not know what they are? The networks, combining, so we don't know which ones they're going through?
That's a great question. It's a really odd name. There's no really good reason for it. It's just a historical artifact, and who knows? I don't know how how they came up with that, but I would actually ignore that term, though it's actually used all the time. But there's nothing hidden about it. Maybe they're referring to how it's hard to interpret how the layers are working. But other than that, I don't have a good answer for that.
Okay. Obscure layers, maybe.
Yeah.
Great. Thank you.
Anything else?
Can you talk about bias in relation to the hidden layers? Isn't there a concern about the lack of interpretability there so that we don't know so easily when we've accidentally done bias?
Yes, exactly. So in that example of the handwritten digit, that was an ideal situation, which actually may not be true in that, we could see that first hidden layer detecting primitive shapes and then the second hidden layer detecting more complicated shapes. But often it's very difficult to interpret what those layers are doing. And so, yeah, people, let's say you're denied a mortgage and an irate customer saying, well, how did you come up with that? Well, a human accountant could give an account of why that person was denied a mortgage. But to look at the neural network that's been trained on data and output that rejection is really difficult because of, like I said, because the network consists of millions or billions of parameters. So yeah, it's a huge research area where people are trying to look at each of the hidden layers to try to get a sense of, what were the steps of reasoning that output a particular response.
Mhm.
And the bias is inherent in the data that you used. So it's not really fair to blame the model. It's the data that was fed into the model, which contains the bias. But the model is to blame because sorry, that's a bit anthropomorphic, but the model is partly to blame because it's just so complicated and it's hard to ask it, well, how did you come up with that prediction? Tim.
Hey, Chris, really, really great presentation. Just a quick question. Who or what determines how many layers are in a model?
That's a great question. That's part of the art of training a model. So it's very experimental. So you start off simple, and then if the model is really struggling to train well, then you add more layers because the neural network needs to be more complicated for your problem. And then you do that incrementally. And that way, so it's really part of the training process. The engineer who's building the model and training the model has to look at the results for a smaller model and say, no, it's not able to solve that problem. So let's add some complexity to the network, make it bigger, because this problem seems particularly hard. And so we have to make the network bigger in order to solve that problem.
Gotcha. Thank you.
Anything else? Any other questions?